right, folks. Today we're going to continue discussing the crystal field model and show, besides understanding how and why it works, okay, we'll then look at what some of the predictions are about the fact that the crystal field model predicts that the d orbitals are going to split and no longer be degenerate, depending on what the structure of the complex is. And that will lead to a bunch of predictions about behavior, about the structure, reactivity, etc. So hopefully we'll get to that today. Before I do that, however, and I'm sorry, but all I have is this here, is to remind me that one of the biggest problems that I find on this section of the course of people getting things wrong has to do with the fact that people don't know how to use the periodic table again, and they don't know how to determine how many d electrons there are in a particular metal oxidation state. If you can't do that, every single thing you do in this part of the course will be wrong, because it's all dependent on how many d electrons we have in a particular system. So if it's a d5 system and you look at your periodic table and you think that iron 3 plus is d6 or iron 3 plus is d4, every prediction and everything you do on the exam will be incorrect. And again, there's no in between. You either have it right or you have it wrong. There's no in between. You have to be able to determine how many d electrons there are in any transition metal in any oxidation state. Okay? If you cannot do that, like I said, you will get every single thing wrong. Now, there are lots of ways to learn how to do that. Okay? The first thing you have to remember is that even though that we have the 3D in the first row of the transition elements, when we're looking at the energies of those orbitals, we have the 3D and then we have the 4s, okay? The 4s orbitals are the ones that get ionized first, okay? So if you have a metal ion that is in the 2 plus oxidation state, it's the 4s or electrons that are going to go out first before you start taking anything out of the 3D. Okay, this is a common misconception that people have, that we're trying to take things out of the 3D first and then out of the 4s. That's not what happens, okay? So that's one thing to know. The other is, it's a good idea to just learn how to use the table itself without having to memorize and figure out every time how many d electrons there are. So I give you one mnemonic device, that's not really the right word, but one suggestion for how to do that. So what you can do, and this is what I did, I worked for a long time on iron in biological systems. And iron has 2 possible oxidation states. Iron, well, has more than that, but has 2 common oxidation states, +3 and +2. So rather than trying to memorize how many electrons there are in all the elements in the periodic table, what I do is just learn that iron 3 plus is d5. Okay, so I have that memorized. Well, from that one piece of information, I can now easily determine what the oxidation states, how many d electrons there are for any element in the d block in any oxidation state, okay? And how is that done? Well, if you go and you have iron 3 plus, and you know that's d5, what does iron 2 plus have to be? By definition. You don't have to think about it, really. It's got one less positive charge, so it must have one more electron, so it's got to be d6. And therefore, we can also say, what would be iron 1? What does it have to be? It has to be d7. And if you have iron 4, what does it have to be? Go the other way. If it was D5 and now it's D4, okay, it was 3 plus oxidation state and now it's a 4 plus oxidation state, it's gonna have 4 d electrons instead of 5. Okay. You can then also go to the left or the right in the periodic table. So if iron 3 plus is D5, I go to the next element to the right, which is cobalt. So what does that have to be? If iron 3 plus is D5, cobalt 3 plus must be what? It's one more element to the right. Got to be D6, okay? If I go one element to the left, which would be manganese 2 plus, okay, 3 plus, excuse me, what does it have to be? It has to be D4, okay? So if you do just, all you really have to memorize is one of them, and from there you should be able to count up and down to determine any oxidation state, and go left to right in the periodic table and determine how many d electrons there are. I don't care how you do it, however, but you must be able to get it right, okay? So as I said, this is extremely common problem. People get problems all wrong because they don't count the d electrons properly. So you have to be able to do that. All right, enough on that lecture. All right, so let's finish up talking about our d orbital splittings in our octahedral geometry and why and what things affect that value of 10dq, which is the splitting energy. Okay, what are the things that are going to affect how big 10dq is, and that in turn will affect whether we're going to be in a high spin or a low spin case. Okay, so I ended up last time talking about the factors, so let's take this up again, that affect 10dq, or delta. And the first one we talked about last time was charge. And I told you that if I gave some examples, that if we go, for example, from a +2 to a +3 oxidation state, the value of 10dq goes up. And typically, in fact, the value of 10dq increases by about 50% for each oxidation state increase. So 10dq goes up by approximately 50% per oxidation state increase. So why is that? Why should that be, given what we understand, what the model, the crystal field model says? The crystal field model says that the reason we have the splitting of those d orbitals is that the metal electron doesn't want to be in those regions of space that point at those negatively charged ligands, because that's going to lead to increased electron-electron repulsion. So, why would an increase of charge make that splitting big? Well, the reason is that as I increase the charge on the metal, what's going to happen to my ligands if they're negatively charged? They're going to get pulled in closer to the nucleus, right? Bond length's going to go down. That means that those metal electrons, those metal d electrons, are going to feel that negatively charged ligand more, because now that negatively charged ligand is closer to where those metal d electrons are. And so as I pull those ligands in, the negative charges in, that makes my crystal field splitting keep getting bigger, because those metal electrons don't want to be in those orbitals. Okay? So charge is a significant factor. Second thing, which we didn't get to, but we already talked about it in fact, is geometry. And as I said, we already talked about this, because I already mentioned that the splitting for a tetrahedral complex, the value of 10dq or delta for a TD complex is roughly half of that of an octahedral complex. So typically speaking, if I look at a tetrahedral complex as compared to an octahedral complex, my 10DQ value is roughly going to be about half as big. And we talked about why that is because in a tetrahedral complex, the ligands, those negatively charged ligands, and the metal d electrons never point directly at each other. They're close, but they're not directly in line with each other. So that leads to correspondingly less crystal field splitting. Okay. Now, we can look at lots of other geometries, but this is the one I want you to remember. What does that imply to you? Remembering that our pairing energy doesn't change a whole lot, okay? And if I were looking at a tetrahedral complex versus an octahedral complex, and I wanted to know, is this going to be high spin or low spin, what does this suggest to you? If 10DQ in a tetrahedral complex is half as big as that of an octahedral complex, and we already said that for an octahedral complex, 10DQ frequently is just about on the same order of magnitude, at least, as a pairing energy. Well, if I slice that in half, what do you think is going to be the situation? It's always going to be high spin, right? We're never going to have 10DQ big enough to make it so that it will be a low spin complex. And so that's an observation that holds true. Tetrahedral complexes, therefore, tetrahedral complexes are always, and I'll put this in quotes because there may be a few cases out there where that is not true, okay? But for everything you're going to see, tetrahedral complexes are always high spin, never low spin. Now I bring this up because on an exam, I might say, give me whether this complex is high spin or low spin for various situations. A metal in this oxidation state, a metal with these ligands, a metal with this geometry or that geometry, okay? And in some cases, I will not tell you what the, whether this complex is high spin or low spin. I get people coming up to me and I'll say, this complex is a tetrahedral complex of cobalt 2+, and what happens when this or that or the other thing? And people come up and say, is this high spin or low spin? Did you forget to tell me which one it is? And the answer is no, I didn't forget to tell you. You should know automatically that if I don't tell you and it's a tetrahedral complex, you know it must be high spin because you know the value of 10DQ is going to be small. Okay? So if you see something where it's a tetrahedral complex and you need to know whether it's high spin or low spin, and I'm not giving you that information, you know that that means, oh, he's not giving it to me because I'm supposed to know that this is always going to be a high spin complex because 10DQ is small. Okay? So keep that in mind. All right. Third thing, periodic properties. Another bit of information. Yes.
So does that mean that OH will always be low spin?
That what?
That OH will always be low spin?
No, doesn't mean that at all. It only means because the value of 10DQ is by definition roughly half of an octahedral complex, that will mean that it has to be high spin. It doesn't at all imply that octahedral complexes have to be low spin, okay? They can be high or low. But if you take that number, which is close to the splitting of the pairing energy, close to the pairing energy, and cut it in half, then it's never going to be as much as the pairing energy, and that's why these are always low, high spin. The converse is certainly not true. Periodic properties, that is to say, where is the element in the periodic table? What we find is that if you go down a column in the periodic table, we find that 10DQ increases. So As we go down a column in the periodic table, (10dq) increases. Example, let's take cobalt hexamine complex, same oxidation as cobalt 3 plus. It has a value of 10dq of about 22,900 wave numbers. We go down one column in the periodic, so that's 3D. Now we go to the 4D, we can go to rhodium. Same 6 ligands, same oxidation state, so we're not changing that. Whoops. 3 plus. Okay. Now 10dq is 34,100 wave numbers. If you go down one more to the 5D level, we got iridium. And iridium with the same set of ligands, 6 of those, same oxidation state. Now it's 40,000 wave numbers. So you can see again that basically for each row, as we go down a row in the periodic table, 10dq is increasing again by about 50%, from going from 3D to 4D and from 4D to 5D. Okay? Why is that?
Is it just because it's easier to polarize the atoms that are bigger, I was thinking? If you go down, the electron shell should be easier to
No,
polarize.
that would change the redox potential, but it wouldn't necessarily change the splitting. Yeah.
So since there's more electrons, the difference between the high stable or the stable orbitals and the more stable orbitals and the less stable orbitals is going to be bigger since there's more repulsions and interactions.
Well, that has to be the case, okay? So what is the actual cause of that? Okay, that is absolutely true. If the value of 10dq is going up, it means the interaction between the d orbitals, between the electrons on the metal and the ligands must be going up. And the reason it goes up is because that the d orbitals are getting what? As I go down the column in the periodic table, what's happening to the distance of those d electrons from the nucleus? They're getting bigger, right? The orbitals are getting bigger as you go down a column in the periodic table. If that orbitals are getting bigger, that means they're getting farther away. That means that they impinge on those negatively charged ligands more. The d orbitals can get closer to the ligands. And that means, by definition then, that the amount of electron-electron repulsion is going to go up. And so that's exactly what we see. So as those d orbitals expand, that d electrons start interacting with those negatively charged ligands more strongly, the value of 10dq increases. And it increases a lot, okay, as you can see, from going from 3D to 4D to 5D. What does that imply to you? Now again, if you assume that pairing energy doesn't change much, and actually that's not strictly true, it does change a little bit, and it turns out that the pairing energy actually gets smaller as you go down a column in the periodic table, but it's not large. But 10dq is getting much, much bigger every time I go down a notch in the periodic table. So what does that suggest?
They're low spin.
That says that probably they're almost, if I go into the second, the 4D and the 5D levels, they're probably going to be low spin. And certainly for the 5D, they are always low spin, okay? So 5D metals are always low spin, and again, I'll put the term always in brackets because it's not absolutely guaranteed. There are a few examples where it's not true, but for generally speaking, 5D metals are always low spin. And 4D metals are mostly low spin. So the only place where we really have a lot of variability, whether it's going to be high spin or low spin, is in the 3D level, okay? In the 3D level, we can have either one of them. That's gonna depend on these other factors that we talked about. By the time you start getting into the fourth row, 4D level or the 5D level, 10DQ is sufficiently large that it's almost always bigger than the pairing energy, and therefore we almost always have only low spin complexes. And again, I will be giving on an exam, let's say there's a platinum 2+ complex, and people are gonna say, is this high spin or low spin, if I'm supposed to figure out how many unpaired electrons there are? And the answer is, I'm not gonna tell you. Because what must be the case, if it's platinum, which is a fourth, fifth row, 5D metal, it has to be low spin. I'm not gonna tell you that it's high spin or low spin. You should know that by definition, if it's in the 5D level, that it's gotta be low spin, okay? Yes?
Well, what if it was 5D and, what if it was, tetrahedral and it was low on the periodic table?
Then you would have a problem and I would tell you,
Okay.
okay? All right, so, those three so far. One more. So, last one we have to talk about is the nature of the ligands. Now, first of all, when we came up with this thought experiment, this Gedanken experiment, that gave us the crystal field model, it says, let's think about what happens if I have a bunch of negative charges and I make them go to the apices of an octahedron. We didn't actually specifically talk about real ligands, however, but you should be able to see, for example, that if I'm talking about a negatively charged ligand like chloride or bromide or thiocyanate or any negatively charged ligand, that's basically the same as just having my negative charges, okay? And if they're arranged at the apices of an octahedron, we can understand why those d orbitals ought to split, okay? But even if the ligands are not actually negatively charged, this stuff still holds. And it holds for the fact, for example, that if I have something like ammonia, okay, it's got a dipole still. There's a negative end to this thing and a positive end to this thing. Same thing with water, okay? It's got a dipole, and there's a negative end to this thing and a positive end to this thing. So it's still going to behave that there's negative charge at the apices of an octahedron, whether the ligand's actually got a full negative charge or whether it's just a dipole. Doesn't really change the whole concept. It says that the metal electrons will try to avoid those negative charges, whether it's a full negative charge or a part of a negative charge. So it turns out that we can create something we call the spectrochemical series. And what this is simply an observation of what happens to 10DQ with a whole bunch of different ligands. This is not something I expect you to memorize, okay? You will either be given it or you will need to know something about the very ends of this spectrochemical series, and I'll talk about that in a moment. But this is basically what happens. So if I start, let's say, with iodide, iodide turns out to have a smaller crystal field splitting, smaller value of 10DQ than bromide, which is less than sulfide, which is less than thiocyanate, which is less than chloride, which is less than nitrate, which is less than fluoride, and hydroxide, and oxalate, water, acetonitrile, ammonia, ethylene diamine, bipyridyl, phenanthroline, nitrite, cyanide, or carbon monoxide. Like I said, you don't have to memorize this thing. This is just, and there are obviously many more ligands than those, okay? This is just a sampling of ligands. What does this say? This means up here, we're talking about 10DQ small, and over here, we're talking about 10DQ large. So we have a bunch of different ligands, and we have very different values of 10DQ for the same oxidation state, the same structure, the same place in the periodic table, but the value of 10DQ can vary tremendously depending on what the ligands are. And if I have iodide ions as my ligands, I have a very small crystal field splitting. And if I have carbon monoxide as my ligands, I have a really big crystal field splitting. Value of 10DQ is big. Now, what you should get out of this, besides the fact that the ligands are important to determining what the value of 10DQ is, you should see that there's an anomaly here. There's a problem. Anybody see what the problem is?
Well, I don't know if it's a problem they're asking about, but what seems weird to me is that fluoride's in the middle, and it's the most electronegative element, so I would have thought fluoride would actually make a smaller 10BQ than iodine, so that was kind of strange to me.
That's probably a reasonable thing, but that's, and it's not unrelated to what I'm going to talk about. What else do you see? Yeah?
Some of the ones that affect the 10DQ most are completely not charged. The whole theory was based on charged particles.
Absolutely right. If you notice this, that most of the negatively charged ligands are what they are mainly weak field, what we call weak field ligands. That is to say, they make value of 10DQ relatively small. They don't cause a lot of splitting. And yet, as you go out here, there's exceptions, mind you. But what you see is that lots of the very strong field ligands, ligands that cause a lot of crystal field splitting, in fact, the ligand that causes the most, which is carbon monoxide, are not charged at all. And they don't even have much of a dipole. Okay, CO doesn't have a very strong dipole. And what dipole it has is reversed. How does CO bind to a metal? Does it bind through the oxygen or does it bind through the carbon? Binds through carbon, doesn't bind through the oxygen. So there's no real negative dipole in CO. There's a problem here. This just doesn't make sense from the crystal field model, okay? This is a phenomenological, that is to say, observational. This is what we see. But can we explain it from the crystal field model? The answer is no. Okay? So this is an example, like we did with the valence bond description, where this simple model doesn't work. It can't explain this. Okay? Right now, all I want you to know is, okay, we know ligands will affect the value of 10DQ, and I want you to have some idea of what weak field ligands look like and what strong field ligands look like. So, and I will usually use the things at the very ends of this spectrochemical series. We're not trying to fool you. If I show you a metal complex with carbon monoxides, you should assume that that crystal field splitting is large. And therefore, it's likely to be what spin? High spin or low spin? It's going to be low spin. If I give you iodide as the ligands, well, you can see that that should give you very little crystal field splitting. And what does that suggest that would likely be the case? It's probably going to be high spin. Okay? So I'll either give you this diagram or I will be picking things that are at the extremes so that you should be able to determine what I'm trying to get at there. Okay? But as to how we can explain it, that's going to have to wait till we go to the molecular orbital theory, and we'll find that we can explain this perfectly well using the molecular orbital model, even though we can't explain it with this nice simple crystal field model. Okay? Now, so this is something you need to remember. Things that are going to affect 10DQ, charge, geometry, periodic properties, and ligands. Okay? You will have a problem on the exam that has something to do with that, I guarantee you. Okay? Something you need to know. And you need to know, basically, some of these extreme cases, what the situation is going to be. If I have tetrahedral it's gonna be high spin. If I have a 5D metal, it's gonna be low spin. If I have carbon monoxide as my ligand, it's gonna be low spin. If I have iodide as my ligand, it's gonna be high spin. Okay. All right, now, before we go on to what are the predictions now that we believe this crystal field model says that the d orbitals are gonna split, and what does that predict for us? I want to be able to go through and determine what the splitting of the d orbitals is going to look like for something other than the two cases we've talked about so far, which was octahedral and tetrahedral. And we can determine the splitting for any geometry whatsoever. Okay? Just applying the same kinds of concepts that we did for the octahedral case. And we will also want to make use of our knowledge of symmetry in this process. So let's talk a little bit about crystal field splitting in other geometries. So, going back, we know in our octahedral case, we've seen this now, okay? By this time, you should have this memorized by heart, okay? Yeah, I know it's the dxz, the dyz, and the dxy down here, and it's the x squared minus y squared and z squared up here for an octahedral case, okay? All right, so let's say we want to determine what's the splitting for a square planar complex, okay? So in a square planar complex, we can do kind of a correlation diagram here and start to think about what's going to happen to this splitting that we did for an octahedral case if I go to a square planar geometry. So in a square planar geometry, what am I going to do? I'm taking away these ligands, these negative charges that are along the z-axis, right? So I just wind up with a square plane, okay? What's that going to do to these orbitals, okay? Well, dz squared was up here in an octahedral case because we have ligands directly along the z-axis, right? But what's going to be true in a square planar case? So it's d4h now. dz squared is not going to be high up anymore. It's not a place where the electron doesn't want to go. In fact, that's where one of the places it does want to go because there are no ligands there anymore. Okay? So what's going to happen is the dz squared is going to go down in energy relative to what it was in the octahedral case. Okay? The dxz and the dyz are also going to become more stable than they were because they had a z component, but I've now taken my z ligands away, okay? So they're also better off than they were before. The metal electrons more likely to want to go into those orbitals, so they're going to go down, and that's going to be the dxz and the dyz, okay? Now, that means then that all that negative charge that we're talking about is now concentrated in the xy plane, because we don't have any z ligands anymore. So what's that going to do? Well, it means that orbitals that have an x component, xy component, are going to become less stable than they were before. So my x squared minus y squared is really now the worst ligand. The electron does not want to be in the x squared minus y squared orbital, because that's the orbital that points directly at those four ligands in square planar geometry. So that's the worst, okay? And then we also have the dxy, which doesn't point directly at the ligands, but it is in the xy plane, and so it's going to become less stable. And where exactly it's going to show up is not entirely clear. It could be here, for example. This could be the dxy over here. Or it might have gone even above the dz squared orbital. We can't really do it without doing a calculation, but it's something that looks like that, okay? We're going to get something, the splitting is going to look like this, and this, and this, and this one down here is going to be xz and yz, and this one will be, let's call it the z squared, call this one the xy, and this is clearly the dx squared minus y squared, like I said. Between these two, there's some ambiguity. Is it this way or that way? I don't know. But it's something that looks like that, yes.
I guess I was wondering why there is ambiguity, because it certainly looks like it's closer to the electron.
No, I'm talking there's no ambiguity between the dz squared orbital. You gotta remember the dz squared orbital does have an xy component. It's got that little belt in the xy plane. It's not just the z axis, okay? Otherwise, it wouldn't be at all ambiguous. But because there is an xy component to it, these are roughly the same, or somewhere in that range. We can't tell exactly. But these have to be together. How do I know that? How do I know that these two can be complete, all these three can be completely independent of each other, but these two have to remain degenerate? Well, the answer is I can have symmetry to tell me that. So if I go to the D4H point group and I look at it, what I find is that in my D4H point group, I'm going to see this in brackets next to one of the irreducible representations. And what does this mean? It means that XZ and YZ or anything like them, and we've talked about that could be the d orbitals, which is what we're talking about now. It can also be the polarizability tensors or whatever, but we're interested in the d orbitals at the moment. This tells me it has to remain degenerate. They have to stay together. I cannot separate these two from each other. So if you try to give me a diagram that looks like that, that's not correct. It can't be that way. These orbitals have to be degenerate. And symmetry is what tells me that that has to be the case. How do I know? I go to the character table for that particular geometry, and I find out what orbitals have to stay together. So wherever I want to put one of them, I have to put the other one. Okay? Let's do one more. Let's say we have a trigonal bipyramidal structure. Okay? And let's think about what might happen for a trigonal bipyramidal structure. Okay? In a trigonal bipyramidal structure, I have Z ligands and I have XY ligands. Okay? So which of the various orbitals do you think would be the worst? Which orbital is most likely the d electrons don't want to be in? Okay, I got dz squared. Anybody have any other alternative? Well, it is in fact the dz squared because of course we have orbitals along that z-axis. We have ligands along that z-axis. And that's the only thing that points directly at those ligands, okay? It's only the z-axis. These don't point really directly at the xy. You gotta remember that's a 90-degree interaction, and this is 120. So the dz squared orbital is gonna be my highest. That's the worst. The other is going to be something that has orbitals in the xy plane. And the one that is we can look at is say, okay, well then it's probably the dx squared minus y squared orbital is the next one. But can I put the dx squared minus y squared, because it's got its orbitals, lobes along the xy axis, can I distinguish that from the xy? And the answer is, well, we'll go to the character table and find out. So what's the point group for something that's in trigonal bipyramidal geometry? D3H. We go to D3H, and you look at it, and what you find is, aha! I see that, which tells me that the dx squared minus y squared and the dxy orbital have to stay together. They're degenerate. So it's not obvious from this picture that they should be degenerate, but symmetry tells us that that is in fact the case. So if I want to put the dx squared minus y squared here, I also have to put the dxy here as well, because they have to stay together, they're degenerate orbitals, okay? And then what else is left now? And so what's going to be the next most stable, the last set of orbitals we have is the xz and the yz. And they don't point directly at anything, okay, so they're the most stable. But are they, in fact, can I separate those two out? And the answer again is if I go to my character table, no matter where I want to place them, if I want to put it over here, let's say, it turns out that if you go to the character table, you also see this. And that tells me that the dxz and the dyz, I can't separate them out. I can't make one here and one over here. They have to be degenerate. So my splitting diagram has to look like this. I have these two degenerate orbitals. If you want to draw it a different way to indicate their degeneracy, they've got the same energy. Then I've got these two orbitals which have the same energy. And then I've got this one orbital by itself. This is the z squared. This is the x squared minus y squared and xy. And this is the xz and the yz. Okay? Yes?
What are the splittings called? It's not 10DQ anymore.
No, it's not called 10DQ anymore, and it's more complicated because you have more than one splitting, okay? We're not gonna worry too much about that at the moment, okay? Because, yes, you're absolutely right, there's gonna be more than one splitting. Now, why is that significant? Well, let's say I have, let's see. Let's say I have, let me think of an example. Let's say I have 4 electrons. No, let's make it 6 electrons, okay? I have 6 electrons, so I have a D6 system. And I want to know, is it a square planar geometry or is it a trigonal bipyramidal geometry, okay? Yes, it's not the same number of ligands, so it's not the greatest choice, but right now I don't care about that. I just want to fill in an appropriate number of electrons, okay? So let's say I got 6 electrons. How are those electrons going to arrange themselves over here? Well, I'm going to do this. They're degenerate, so they don't want to go up to anything, and then the next one comes up is over here.
How do you know that they're not close enough that they don't?
They're not degenerate, you don't absolutely know it, but they don't have to be, and in fact, they aren't that close to each other. Okay? Okay, so unless you know that they're degenerate, you don't assume that they are.
Oh, yeah,
Okay.
I just thought maybe they're closer than pairing.
No, they're still bigger than the pairing energy. Okay? I mean, these gaps are bigger than the pairing energy. What would the situation look like over here? If this happened to be the same 6 electrons?
Would be highest then.
It would have to go like this, right? How many unpaired electrons there are over here? 0. How many unpaired electrons over there? 2. That's a physical, observable thing we could go determine, okay? We could determine that from later on. We'll talk about magnetic susceptibility or electron spin resonance spectroscopy. We can determine which one it is, and that means that this can tell us which of these geometries it has to be present. If I find 2 unpaired electrons, it can't be this, it has to be that. Okay? So that's the basic reason we're going over some of these other geometries, is because those geometries are going to give us some predictions about what can happen with, depending on how many d electrons we have in that particular system. So what I want you to do is, and this is on the bulletin board again outside of CSL 410, is we've done square planar and trigonal bipyramidal, but you should do them yourself, okay? Make sure that you can understand what I did. And to make sure of that, I want you to predict what's the structure, the splitting I should say, for linear complexes, trigonal planar, square pyramidal, etc., or anything else you can think of, okay? That happens to be all I can think of at the moment. But that's 5 different geometries that we have the square planar, we've got trigonal bipyramidal, and we've got these 4 over here, and we've got octahedral and tetrahedral. So that's a whole bunch of different structures, all of which we can predict how the d orbitals are going to split, okay? Using a combination of the concept of the crystal field model and symmetry. Okay, so you need to go through and do those. You will, for sure, get an example of that on the exam. Okay? All right. But of course, again, if I ask you some question and you don't know how many d electrons there are, you're not going to get anywhere with it, okay? You have to be able to determine that. All right, yes.
If you had trigonal bipyramidal with 6 electrons still, but this time one of the ligands was different, would the difference in energy be so small anyway that it would still be high spin?
Right, once again, this is all qualitative. You can't make quantitative predictions about small changes, okay? We're not looking at that level. All right. So, what I want to then do, as I said, is to look at some predictions about certain kinds of things and how this model is going to predict those things. And what we're going to start with is, let's see, what should I call this now? Effects of the ligand crystal field splitting. All right, so the first thing we're going to look at is we're going to look at ionic radius. Okay, so we're going to go across the periodic table, and we're going to look at what happens to the ionic radius of different elements in the periodic table, and see if we can explain the observations that we actually make about what the ionic radius happens to be. So we're going to plot ionic radius versus element. And I'm going to start with calcium and move across the first row of the periodic table. So I'm going to start with calcium, and then I go to scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. And we're going to assume for the moment that these are high-spin divalent metals. Okay. What we expect to find, if you look at what happens in the main group of the periodic table, is typically that the ionic radius should go down as we go across the periodic table. The ions get smaller as we go across the periodic table. That's the standard expectation of what happens to the ionic radius in this main group of the periodic table. Why is that? Well, it's related to the concept of shielding. So as you go across the periodic table, we go from left to right. What's happening to the number of protons in the nucleus is going up, right? We're adding one more proton. Which, of course, we're also adding one more electron. And so what happens, though, is that each one of the protons we add and each one of the electrons, they don't shield, the electrons don't shield each other perfectly. That is to say, you would think, well, okay, I added a proton, but I also added an electron, so the relative plus to minus isn't changing much. But the ionic radius actually gets smaller because those electrons that we're adding don't shield each other very well, and so as the protons increase, their pull on the electrons actually gets larger each time I add a proton than you would expect it to be. Okay, I'm not going to go into shielding. It's something you, once again, you should have had in freshman chemistry. But that's what you expect to find. Okay? Now, what you actually see is the following, and we'll stop there. What you actually see is calcium falls on the line. Scandium is off, it's below. Titanium is off, it's below. Vanadium is off actually the most. It's way down here someplace, okay? Off the line. Chromium goes back up again. Manganese turns out to be back on the line. And then iron goes down, cobalt goes down, nickel goes down, copper starts to come back up again, and zinc falls back on the line. So you have this sort of biphasic, not a very good picture here, two humps, if you will, where certain elements fall on the expected theoretical line, and then a whole bunch of elements fall off that line, and they're always below the line. That is to say, their ionic radius is smaller than we expect it to be. Okay? Why that is, we'll talk about next time. Okay.